we are going to start the second part of session 3, and we're going to talk about P4, a couple of papers on P4. So we have Belma Turkovic from TU Delft, and she's going to talk about fast network congestion detection and avoidance using P4.
So good afternoon. I'm going to present our work about fast congestion detection and avoidance using P4. It's envisioned that in the future, networks are going to support a much wider range of services than application existing today. So, for example, one of these application domains is the tactile internet, and the network requirements are actually listed on this slide. So if we want to support transport of touch over the internet, we need to satisfy some very strict requirements. For example, very low latency. That's in the range of 1 millisecond, very low jitter. But on the other hand, we have high bandwidth and high reliability. So while there are certain prediction algorithms that can somewhat relax the latency requirements, we still need very consistent feedback and maximum latency bound in order for such systems to be stable. So the main idea that we had was to see how we can actually control the maximum delay, so to actually bound it to a certain value and reduce the jitter. So in every network, packet usually encounters 4 different types of delay. So the first 2, propagation and transmission delay, are always, so they're functions of physical speed and physical distance, or for example, the data rate or the packet length. And thus on a certain path, they will be constant and won't change. On the other hand, processing delay and queuing delay actually depend on the current state of the network, and are thus the variable parts that need to be limited and controlled in order for such new services to be possible. So to actually have the limited and guarantee the delay that we actually already talked about. So the main contributor to the queuing delay is actually congestion that occurs when a network node is processing more data that the network node is receiving and needs to process more data than it can handle. So usually the output links don't have enough bandwidth, and thus the packets need to be buffered before they can be transmitted. And this was like the main factor that we actually focused in our paper. So there are a lot of existing approaches to congestion control. Some of the most important are actually listed on this slide. So we can do congestion control at the transport layer. All these algorithms actually work by adjusting the sending rate at the traffic source. But this is actually not feasible for all types of traffic. So for example, if we have haptic data, we actually don't want to buffer it at the traffic source because we want to send it as fast as possible in order to actually reduce the end-to-end delay for every packet that's being processed. The other approaches actually use SDN. So SDN, with the central controller that actually has the overview of the whole network, it's way easier to actually detect congestion in the network, and then we can do one of these 2 things. So we can either use resource reservation, or we can reroute the affected traffic. So the controller actually creates an overview of the current network state, and then using some monitoring interval, it will actually detect congestion and then pre-configure the new paths to reroute the traffic. So these approaches have 2 main problems. The first problem is long detection time. So detection time actually depends either on the RTT in case of transport protocols or on the monitoring interval if we use SDN approach. And depending on the monitoring interval that was configured, this will actually influence usefulness of the getter data. So if the monitoring interval is too big, we will maybe fail to actually notice some changes in the network. If the monitoring interval is too low, then we might overwhelm the network with monitoring packets, and of course we are sending packets that are not actually useful, and thus reducing the utilization. The other problem is the long reaction time. So the reaction time actually depends also either on the RTT, because transport protocols need to actually receive feedback, or the delay between the controller and all the switches in the path. So in case of an SDN solution, if we want to reroute the traffic, we need to reconfigure all the switches in the path to the new path. So during all this time, the packets are still processed by these congested nodes, and they are still, so we still have an increase in the per packet delay, which can cause possible instability for certain services, like the tactile services I mentioned. So for example, teleoperation services that have a really closed control loop. So the problem that we actually wanted to solve in this paper was to avoid the automation artifacts, how to enable congestion control and avoidance in the network nodes themselves instead of at the source or via the controller. So we wanted to actually be faster by doing it in the network itself. And, well, first problem that we had to address is that, well, current network nodes, network switches and routers have a fixed, well-known behavior, and they only support a fixed set of protocols. So adding new possibilities to measure or control the data path is actually impossible without the new data plane programming techniques. So in our paper, we actually decided to use P4 in order to actually enable some advanced mechanisms in the data plane itself. So programming languages as P4 actually enable us to program the switches themselves. So we program the data plane. And this is like a big picture of our solution. So we proposed a hierarchical control plane where we have a central controller that actually acts as a typical SDN controller. He does, so he configures and monitors different paths for different traffic classes. And we identify, so in our solution, we only use 2 different traffic classes. So one was the standard routing module that actually forwarded the best effort traffic, and the other was the tactile internet module that actually only configured the paths for the low latency traffic. So the central controller actually monitors the network, creates an overview, and configures the initial paths. The other part was the local controller that was actually running on the switches themselves. And the main purpose of this part was to actually reduce congestion detection and reaction times. So we actually, in the data plane, we actually detected both the congestion and reacted to it by rerouting the flows, while without the help from the central controller. So the central controller only provided some initial configuration for the switches. So the module that we actually implemented was, so when data packets were processed to the switch, every node that actually had this module was collecting statistics for low latency flows. We used these first 4. So for every data packet, the switch actually, on the data itself, calculates what the processing, queuing, and queuing length was. And then based on these values, it will detect whether that switch is actually congested or not. So the central controller actually configures a set of thresholds and then the local congestion detection model actually checks whether these metadata actually exceeds the pre-configured thresholds, and if it does, the congestion is detected. Of course, we also used, so in order to actually avoid short-term fluctuations, we actually could also configure the number of packets, so the number of consequent packets that needs to actually exceed the thresholds in order for the congestion to be detected. So we actually want to check whether the queue is building up. So the goal was to actually detect the queue buildup before the queues are actually filled and like higher delays actually caused. So that was like the detection part. The other part is congestion avoidance. So in order to actually implement congestion avoidance, we use multiple paths. So for example, when a new host appears, for example T1, and wants to set up a new flow, his packet in is going to first be forwarded to the central controller that then configures 2 paths. Well, the central controller first calculates k shortest paths, sorts them according to the end-to-end delay, and then uses the first 2 to actually and pre-configures these values in the data path. Of course, we had to take into account that after like S1, no same links are used for the backup and direct path. So we are actually going to show this on an example. So for example, if the blue path is actually the primary path and the red one is the backup path, and now if the switch 1 actually detects the congestion, so when the values actually exceed the thresholds, he will know that the better path actually goes through this switch to switch S4, and the only thing that he needs to do is actually change the output port for that traffic flow to point to S4. So this is just one track data. So this is just like changing one table entry in the table, and it's done locally. So this switch can immediately react, and the traffic is rerouted instantly without any cause in the delay. Alternatively, if, for example, switch S5 detects congestion, he doesn't have a better route that actually goes through it, so he actually will inform switch S3 by sending me a small control packet. Then S3 actually checks whether it has a better route. Because it also doesn't, it will send it back to S1, and S1 will change the output port to point to S4, avoiding switch S5. So in order to do this rerouting in the data plane using P4, we are left with two choices, and we actually compared and implemented both of them. So the first is to actually add both entries to a same table, and then match based on some metadata that actually indicates whether the flow is congested or not. So in this case, we actually need to keep a set of metadata for every flow that actually indicates whether that flow is congested or not, and then match based on that metadata in every table. Alternatively, what we can do is we can actually create small packet digest notifications. So these are like very small packets that only contain important information, and then these small notifications are sent to an actual small control module that's running on that switch, and then that local listener module can track the flows and actually change the table entries in the switches themselves. So we have evaluated both of these options using first Mininet and the software switch, and then using Metronome smart network cards that actually support P4. Our testbed actually consists of 4 servers that have 4, where each of them actually has one network card that actually supports P4. And in Mininet, we used like the same topology that I showed previously. So these are some of the results. First, so these are the results from, for example, Mininet. And we can see that, so the first 3 actually are the probing scenarios. So the typical SDN scenario where the controller actually sends monitoring packets every 5 seconds, 3 seconds, or 1 second. And based on that data, detects whether the flows are congested or not. And we can see how the detection time changed according to different additional traffic. So because it was Mininet, we actually configured that maximum throughput of the output links was around 200. So we can see that the data plane approaches here actually have the lowest detection time, because they were actually able to detect it immediately in the data plane and switch. And so this actually shows the amount of traffic that was forwarded on the backup path. So we can see that based on the different thresholds set, we can have, for example, in this case, we can have the switch every time. So because Mininet has certain fluctuations, because it's a software environment, delay actually varied, and then because the threshold were set too low, the switches always detected congestion and switched. And of course, as we increase the threshold, we can actually obtain a very nice value. So here we can see that this, for example, will only switch when there's actually congestion. And we'll still have a huge number of traffic that's actually forwarded on the backup path. So these are the values from metronome cards. So we can see also the differences in average delay. As we can see, these are also like the case when there is no congestion control and the probing scenarios. But interesting here, the data plane approaches can actually keep the average delay low and constant, but as we can see, this one actually has a higher value. So this one was actually the one that implemented everything directly in the data plane, and it had some initial additional delay because in order to actually support this in P4, we had to implement more tables and apply more tables. So the processing in the switches was actually a bit more complex than in the other approaches. So we had some initial problems with latency, but the values will stay constant. And there are like 4 switches that process this. So these are the values for the loss, and we can also see that the data plane approaches can actually keep the loss at 0 in this case, because before the queues are actually filled, the switches already switch to a better pad that's not congested, and thus the switches never have to drop packets. And of course, now these are the values for maximum and RTT and jitter. So in case of metronome, the results were for maximum delay were not, so it could keep the values a bit down, as we can see, but the problem was that also in our, at least, that in our solution, the metronome actually detected it a bit slower than, for example, the Mininet one. But it was still actually able to keep it lower than the approaches that use probing or no congestion control. And these are the values for jitter. So the data plane direct one was actually able to kind of keep it down. Not ideally, but anyway, to conclude, we presented a solution that actually allows fast congestion detection in the data plane using P4. So our solution offers 2 main advantages. First, detection time is reduced, and congestion is detected per each flow. So only flows that are actually affected and for which the queue buildup was actually observed are rerouted. And of course, reaction time is also minimized as the local control module actually intervenes by configuring a better route immediately. It's possible to extend this to a hybrid network where only some nodes are programmed by placing the P4 nodes at a specific locations where we actually expect congestion to occur and that need to be monitored. Thank you.
Thank you. Any question?
The overview of the whole network. So it can actually then know what the best paths are. So it has a view of the central network.
But at some point, does it hand off control to the local controllers, or how is the interaction between them?
So the central controller actually configures the table entries. So the backup and the primary and the backup path, and the thresholds that the local controller uses. So these values are set. So the thresholds are actually set in some registers. So the central controller actually has to set these values and the primary and backup path, but nothing else.
Okay, so there's like an independence between the local. So the local control can do only things within the scope that the central.
Yeah, but it can only do scopes like for one switch. So it can know whether it's congested, and then either switch to a better path, or it can inform the previous switch in the path that it's congested and it shouldn't forward traffic to it.
Okay. Am I allowed to ask more? One more. One more. Wow. Okay, slide 10, please. Okay, so in terms of time, can you talk about sampling, calculating, deciding, and what's the relevance of everything? In terms of how long is the queue and for this. So I can't do this in one question. Anyway, you have the queue. So do you have distinct times in which you sample the queue, or do you just wait to see if the queue is in overflow in order to calculate something?
Okay, so it depends on the actual switch. So for example, the software switch actually can calculate the processing at the ingress control part and the queuing port.
Okay.
For example, metronome actually doesn't really do it like that. In metronome, we can actually place timestamps wherever we want. And what we can do is, like, when the switch leaves the, when the packet actually leaves the car, the switch can actually again timestamp it. So we used, for example, these two. It's limited, so it actually depends on the hardware where exactly we can timestamp it. But yeah, at least some of these possibilities are actually possible.
So can you go to your topology slide, please? Yeah. Okay. So this is like a very simple topology and not like a real data center factory stuff. So in a larger topology, so I understand that a switch 1 reroutes from the blue part to the red part if it detects congestion on the blue part. So if later on you have a more complex traffic and topology, if the red path becomes congested, maybe it will switch to the blue path again. So how do you avoid, let's say, these ping pongs in a larger topology and like the effects that the reordering gets on the end-to-end congestion control?
So first, the topology is a bit smaller because we used Mininet, and software switches are actually kind of processing intensive, so we actually couldn't build a bigger network. But yes, I actually agree that in a bigger network it can cause like switches. So in case when it switches from a blue pad to the red pad, the central controller will also notice that, and he will actually configure the new backup path for this one, because he knows he monitors the network constantly.
But that is like 3 seconds, right? So that is your 3-second
yes.
interval.
Yeah, but like we don't want to switch that often. True. So it will have some problems. Yeah. So
during he reconfigures the backup.
So this one actually will reconfigure to the backup path. But yeah, so then in the next monitoring interval, the central controller will notice that this one is actually switched and will configure the second backup path instead of the red one. So we might actually, he might configure the blue path again. And then this will be the backup path and it will switch to that one. I'm not actually understanding the question.
We have more questions.
Is your solution referred to data center networks, right? Or is no? Because so for data center networking, you're trying also to push like switches with very shallow buffers that they have maybe 5-6 packets only. So I'm interested to know how this system will work and might react if you have like a very small buffer to sustain like low latency application. Because do you have time to, you see what I mean, like to realize that you have like congestion, but you don't have much space because the factory is like a very small buffer.
Well, it would detect. So if you set the threshold to a very small number of packets, it will actually detect that there is an increase, which actually also, by increasing the number of subsequent packets that need to be affected, we can actually also like affect change. Well, we can also fight like, well, not have like constant switches, because yeah, that will actually, because if we actually set that threshold to low, for example 2 or 3 packets, we actually might really have problems that we will immediately switch all the time. But yeah, so if the total amount is actually 5 packets, it's quite little. So there might be some degradation by constantly switching.
One very last question.
What happens if the congestion is on the link from S7 to T2? But other schemes handle that. So what happens here?
but like then it will still not. Yeah, so well, for some applications, delaying the traffic at the source is actually a good approach. I'm not saying it isn't, but for some applications, for example, the haptic data, we want to send as fast as possible. So then the end-to-end delay per packet will actually be increased. But yeah, so if it's, for example, a different applications, I still think that it's good to actually also use the traditional transfer protocols. So there. Yeah, but like they're also separate in this case. So like I will never not. So I'm only using this approach for a low latency traffic. That's so when I identify the flow as a tactile flow. For all the other flows that are best effort flows, they're processed in the normal way, and they actually won't be switched.
We can continue that after. So thank you very much again. Your laptop, sorry. Okay, so last paper of the day, we have Marco Chiesa from KTH, who's going to talk again about P4, in particular about supporting emerging applications with low latency failover in P4.
Just 1 second, it's taking a bit to load here. Okay. So guaranteeing low latency and achieving high availability is critical for running a network today. So in this talk, we'll talk about these two aspects in the context of programmable data planes. So P4 is one of the emerging programming data planes, programming languages for packet processing systems that comes with great promises for enhancing network flexibility and network automation. So network operators can program the behavior of the forwarding plane with a high-level abstraction language that is based on the PISA pipeline architecture. And compilers then take this P4 program and compile it into the physical devices. As a reminder of how a PISA pipeline architecture looks like, so it is a sequence of stages. The first stage is a parser that extracts the relevant portion of the header and passes this information to the next stages. So it passes it to the ingress pipeline initially. So the ingress pipeline is a sequence of stages, match action stages, that process the packets. And then the packet is passed to a crossbar that identifies the designated outgoing ports. And then again, it's passed to the egress pipeline, which finally sends the packet either through an outgoing port or it recirculates the packets through the pipeline. So today there exist already several vendors that produce and sell P4 switches. And in order to be price and performance competitive with the ASIC counterparts, they still have to achieve some compromise between the expressiveness of the pipeline and the performance. So for instance, today's P4-based switches, the P4 programming language does not allow to use constructs such as for loops, and the stages in the pipeline, they are often limited both in the type of actions that can be performed and the amount of resources, such as SRAM and TCAM memory. So network flexibility and automation is great, but what about network performance? So two of the critical aspects of running today's network relates to guaranteeing low communication delay and a high availability in a network. And we'll have two talks in the routing session tomorrow tackling these two problems. So when we look at high availability, this means that we want, as network operators, to provide a certain service level of performance, even in the presence of failures in the network. So common common wisdom states that, in general, in order to achieve this high availability, it is necessary to a certain extent to over-provision the network and make use of faster route local mechanisms. So what is a faster route mechanism? Faster route is a networking mechanism that allows to quickly reroute packets in a network without having to invoke the control plane. So the way faster route works is simple. So in faster route, there is a control plane that will configure a set of primary and backup ports in the network. So the switches will use the primary paths as long as failures occurs in the network. When a switch detects a failure, then it immediately uses the local backup rules to reroute the packets based on the backup rules. So in this way, as I said, the network downtime typically can be reduced to the order of 50 milliseconds, and it doesn't require to invoke the slower control plane, which takes much longer to reconverge the network to a stable state. Thus, faster route supports high availability in a network. So on the other side, the inherent nature of faster route imposes a drawback. So since the failures are not known at the time when the faster route rules are computed, it may be necessary to pre-install in the switches all possible backup rules for a certain amount of failures, which can be extremely large in the network. So this state may easily exceed the capacity of the memory capacity in the switches and do not fit into the pipeline. So the natural question that we asked that we tried to answer in this talk was, how do we actually support high availability in programmable networks, and in particularly in the P4 programming language? So there are two aspects that we have to consider when we look into faster route in P4. The first aspect relates to the computation of the backup rules. So in a network, typically there is a controller or a network operator will compute these backup rules that maps flows to sequences of ports. So the sequences of ports are called faster route actions. And typically, the semantic of a faster route action is that a packet should be sent to the first active port. So those faster route actions typically comes with some guarantees in terms of the number of failures that can be sustained in a network without requiring the control plane to reconverge. So the second aspect relates to the realization of the faster route actions into the P4 pipeline. So in this talk, I will only consider the second part of the problem. So I will assume that there is a controller that computes the faster route rules and provides these faster route actions as input. And our task is to implement those faster route actions in the P4 pipeline. So the problem here is that the P4 programming languages does not have any inbuilt support for faster route, leaving it open to the network operator the implementation of faster route actions in the pipeline. So on the bright side, P4 has a high network programmability, and this can be used to actually find different ways to implement these faster route actions in the pipeline. And we will look at some of these possibilities. So to start exploring the benefits of programmabilities to implement faster route, we'll consider this simple example. So we have faster route actions that we want to implement. So each faster route action is obtained by the previous one by shifting the sequence 1 to the left. We call this type of faster route action circular faster route actions. So one simple way to implement these faster route actions in the P4 pipeline is to use packet recirculations. So we will recirculate a packet through the packet processing pipeline until we find an active port. So the mechanism is simple. We initially send the packet through its designated primary ports. So in this example, we want to send a packet using the second faster route action. So in the absence of failures, the packet is sent on the primary outgoing port. And as soon as there is a failure, some metadata information about the next outgoing port is stored in the packet metadata, and the packet is being recirculated. So the obvious drawback of this approach is that when we have multiple failures, packets have to be recirculated multiple times through the packet processing pipelines, and this creates a sort of self-induced incas that leads to throughput degradation. So the first requirement for a faster route primitive is that we want to support high throughput, which means we don't want a throughput reduction unless there is no enough bandwidth on the outgoing ports. So an orthogonal approach to implement faster route in P4 would be to iteratively check over multiple stages which is the first active port. So here we basically check over multiple stages the status of the different ports. So the first row is the implementation, represent the implementation of the first faster route rule, and we have one row for each faster route rule. So if we consider the second one, in the absence of failures, we will already find the first active port in the first stage. So as soon as, if you assume that the port 2 will fail, then in order to find the second one, which is port 3, we'll have to go to the second stage and so over. So the obvious drawback of this approach is that there is both increased latency, as we have to traverse multiple stages in the packet processing pipeline, as well as wasted resources at each stage, since we may not be able to reuse TCAM and SRAM memory on those stages that were so they will basically be wasted. So the second requirement for a faster route primitive is that we want to have low latency, which means packets should, so the packet processing time shouldn't depend on the number of failed links that we have on the switch. To keep latency as stable as possible, we need to resort to some level of parallelism. One natural structure that we have in a switch is a TCAM memory that we can try to exploit in order to find the first active port in a parallel way. So the approach works as follows. So suppose we want to implement the second faster route action that is 2, 3, 4, 1. So in the packet metadata, we store an identifier of the faster route action that we want to implement. And then we assume there is a P4 register where we store the status of the ports. So the semantic is the following one. The bit I in the P4 register denote whether the port I is active or not. So if the bit is set to 1, the port is active. If it is to 0, the port is not active. So the approach, this naive approach, is very simple. So we take the port status and we append it to the packet metadata, and we feed this information as inputs to a TCAM table that is constructed as follows. So we have one entry for each port in the faster route sequence, and we preserve the mapping where the leftmost port in the sequence is the top entry in the TCAM table. Since the TCAM table will return the top first matching entry, first top matching entry. So in order now to find which is the first active port, we need to match on the port status. And now, in the absence of failure, if we want to send a packet using the second faster route action, we just write in the packet header that we want to use this faster route action, and in the absence of failures, we will hit the top first matching entry. So if there are failures, we just need to update one bit in the port status, and automatically we will match, in this case, the second entry, or if there are two failures, the third entry. And this is just one TCAM access in the table. So if we want to implement all the faster route, the 4 faster route action, we can duplicate this approach, and we will have different TCAM entries for each faster route action. So this approach supports efficient rerouting, which means that as soon as the switch detects a failed link, then packets will be immediately rerouted to the first active port. And this is supported by simply updating the port status in the P4 register. But we mentioned before that the P4 switches, they tend to have limited resources at each single stage. So we still want to keep the state that we need to implement these faster route actions as small as possible. So we investigated how much space do we need to implement this faster route action in practice. So we consider as input a switch with k ports, and we consider 10 circular set of fast reroute actions. So we consider circular set of fast reroute action as this has been shown to, this has been used in several fast reroute mechanisms that are robust to multiple failures, such as F10 for data center networks and k-arc disjoint spanning trees. So with this naive TCAM approach, each single circular fast reroute action requires k-squared number of TCAM entries. And if we look at switches with 24 and 48 ports, then the amount of TCAM entries is already significant. So what we suggested is a way of encoding and compressing these for fast reroute actions and the representation in the TCAM tables so as to minimize the space that is needed in the packet pipeline, in the packet processing pipeline. So the mechanism is simple. We still have the same packet header with the port status appended to the packet header metadata. But now we have an additional metadata field, which is called fast reroute ports. So this field maps, each bit in this field is mapped to a port of the switch. So let's consider an example in which we want to implement the second fast reroute action, 2341. So now we will set a bit to 1 in this field if we want to use that port. Otherwise, we'll set it to 0. So in this example, if we want to implement 2341, we will set the first bit to 0 since we don't want to use the first port. And then we will set the next 4 bits to 1 since we want to check ports 2, 3, 4, 1. And then we'll set the remaining bits to 0. So we can store this information in SRAM memory. And as soon as we receive a packet, we can match the fast reroute ID and add this information into the packet metadata. So once we do this, we can feed this information into a TCAM table. So the TCAM table has 1 entry per bit in the fast reroute ports. And what we are basically, what we want to do is to map each single bit using the mapping that we used before to the outgoing port where we want to send the packet. So similar to what we had before, now we will use the port status to find the first active port. So if in the absence of failures, if we are sending a packet with this fast reroute action number 2, we will immediately match the second TCAM entry in the table, and we will send the packet to the second outgoing port. So as soon as we have failures, we use the same technique. We update the P4 register status of the second port, for instance, in this case, of the second port to 0, and the packet will be automatically matched the entry that will send the packet to the third port. And we can use the same process if we have multiple failures. So the key insight here is that we are using the same TCAM entry for different fast reroute actions. So we may considerably save a lot of TCAM space in the packet processing pipeline. So to understand how much space we save compared to the naive approach, this approach with this encoding actually requires only 2k-1 number of TCAM entries to implement one circular fast reroute sequence. So if we look at the same switches that we had before, this means a reduction in the number of TCAM entries of more than 90%. Our primitive is expressive enough to support a variety of existing fast reroute mechanisms that are based on circular fast reroute sequences. So to mention some of these mechanisms, we have F10, which has been proposed for data center networks, and it's resilient to multiple link failures in the data center, as well as node failures. Depth-first search, which are graph-based exploration fast reroute mechanisms that explore the network as in a depth-first search algorithm. And then spanning k-arc disjoint fast reroute mechanisms. So all of these type of algorithms use some sort of circular fast reroute actions. So we build a proof of concept implementing the DFS mechanism. And we ran some very preliminary evaluation on our software switch with Mininet. And we plan to actually run more evaluation on a physical switch that we just got recently. So we still don't have the results for a physical switch. So the nice thing about the implementation of the DFS faster route mechanism is that in the DFS, what you do is you receive a packet from a parent node, then you want to explore all the children node, and only then you want to send the packet back to your parent. But you don't know the parent as long as a failure happens in the network. So you will not be able, when you program when you install the rules in your TCAM entries, in your forwarding state, you won't be able to predict who is the parent node. So this requires some additional programming requires to program this pipeline with a little bit more careful, and we used some additional P4 programmability to do this. And we compared a plain open flow implementation of DFS with a P4 one, and we observed a reduction in the number of forwarding of TCAM entries of 99.7%. So we argue that P4 compilers should offer a faster route primitive that relieves operators from the burden of realizing faster route action in practice. And we believe that that the compilers can actually implement those faster route actions in different ways, depending on what one needs to be optimized and what is clearly the target device. So to summarize, faster route has been widely used to achieve high availability in the networks. And yet, the emerging data plane programming languages do not have an inbuilt construct that can be used to implement these faster route actions in the pipeline. So we proposed a relatively simple TCAM-based faster route primitive that is based on an encoding using a packet metadata, and it doesn't require any faster route tailored hardware support beyond general purpose TCAM memory. So in the future work, we plan to optimize the mapping computation and to evaluate on real switches. So thank you for your attention.
We have questions. Okay, we can start from here.
Hi, thank you. This is excellent. After the port has failed and you switch the path, let's say that port is restored. How do you restore the path back?
So you need to set the bit back to 1.
Yeah.
So you need to set the bit back to 1. How do we trigger it? So it depends. So at the moment, we assume that there is a P4 register that where we can look into the status of the ports. We didn't implement it, and I don't think it is supported at the moment. So, but for us, it seems like this is the minimal assumption. If you want to reroute packets based on the status of the ports, you need this information somewhere, and we have this register where we can get access to this information. So then it depends. As soon as the switch detects that the link is up again, it can set again the bit to 1, and automatically packets will be routed on the original path. Thanks.
Thanks. Thank you. Just a quick question. Could you roll back to where you append the where you that's the one. So first you append to the packet. I'm asking, right? I don't know if I got it right. First you're appending to the packet the port status, and later on you append in front of that the FRR ports. Am I correct? So that's the. Okay, so my question is, I'm not saying it's bad. I'm just asking to see if I got this right. So let's say with a 32-port switch, you would end up appending 64-bit to any incoming packet. In the packet metadata. So it does it or does it not affect the switch throughput?
depends on the physical system, the physical packet processing system that you use. So at the moment, we don't have an evaluation on the P4 switch, on a physical P4 switch, but
It depends how the mechanism of appending something to the packet occurs inside the
so when you need to, when you're appending this information in the packet head, in the packet metadata, then you want to match it. So it depends, for instance, on what is the width of the TCAM tables that you have in your packet pipeline. If the width of the TCAM table is too small and the number of ports in the switch is like 1,000, then you may not be able to match them, all of them. So it really depends on the underlying device that you have, that you actually have. So we plan to run some additional evaluation on physical switches, on a physical P4 switch soon. So we will investigate this a little bit more. Thank you.
Any more questions? If there's no more questions, let's thank again all the speakers. We're almost in perfect time for the panel. It will start now. Thanks.